Hi everyone, welcome to this session which is on the topic of Algo and BGP Classful transport. My name's Julian Bluchek. So before we talk about the main part of the talk, here's an overview of the segment routing landscape. As you know, segment routing has been around for about 8 years now in terms of IETF drafts, and it's been deployed in many networks worldwide. Now, if you look at the main branches of this layout, then one of the branches on the right-hand side is traffic engineering, and people can do segment routing, traffic engineering using distributed TE. But nowadays, people increasingly are using central controllers, and that lends itself very much to self-driving networks, things like automated congestion avoidance, automated self-healing, and automated egress peering engineering. And then the other branch on the left-hand side is shortest path routing. And people often use SR as a vehicle for migrating away from LDP using the SR version of shortest path routing. And also an aspect of shortest path routing is Algo, which we'll be talking about a lot during this session. And then BGP Classful transport, that's another topic for today, but it's not in this diagram because this diagram is talking more about what happens within a given domain. Well, BGP Classful transport is talking about how we glue different domains together. So with that, I'll go on to the first of the topics I'm going to cover, which is applications of Algo. And what I'll be talking about in particular is the applications and use cases of Algo. If you want to know more about the underlying protocol machinery, how Algo definitions are communicated using the IGP, then I'd refer you to Shraddha's talk from NANOG 81. So let's have a look at this first example of Algo. And so what we've got is a topology where I'm assuming that the metrics are the same on each link within the topology. And we've got the normal IGP topology, which I call the gray topology. And all of the nodes in the diagram are members of that. And then we have two Algos set up in this network. We have the blue Algo, the routers on the top part of the diagram are members of that. And then you've got the other routers, which are members of the red Algo. And from the SID point of view, each node will have a different node SID for each topology that it's a member of. And so by way of example, we can look at PE3, and it's a member of the default gray topology. And so there's a SID associated with that, the value 3003 in this example. And then it's a member of the blue Algo, and so it's got a SID associated with that, with the value 1003. And both of those are associated with its loopback address, which you can see is 10.0.0.3. Then, in a similar vein, PE4, that's a member of the default gray topology, and its SID associated with that is 3004. And then it's a member of the red Algo, and so it has a SID associated with that, which is 2004. And all of the information necessary for the other nodes to know these SID values is communicated via IGP extensions. And so all of the nodes in the network will know these different SID values. And each of these nodes will also have different SID values as well, but they're just not shown in the diagram for reasons of clarity. And then what happens is that each node performs separate SPF calculations, shortest path first calculations, for each topology that it's a member of. And so if you take PE1 as an example, it's doing one set of SPF calculations as a consequence of its membership of the gray topology, and a completely separate set of SPF calculations as a consequence of its membership of the blue Algo. And in general, or at least sometimes, the outcomes of those calculations could be different because the topologies are different. And so now we can look at an example of sending traffic across these various topologies. So first of all, let's have a look at an example where PE1 wants to send traffic using the vanilla gray topology. So, you know, we're not too fussed about what path this traffic takes across the network. And so PE1 launching traffic into this gray topology uses the node SID associated with the destination node, which for the gray topology is 3003, as you can see here. And so PE1, when it did its SPF calculations in the context of the grey topology, realized that it has two shortest path neighbors towards destination PE3, those being P1 and P2. And so it ECMPs the traffic across those two next hops. Likewise, P2 can see P3 and P4 as next neighbors, as does P1, and so the ECMP across P3 and P4. And so you can see the traffic makes its way from PE1 to PE3 across the network using these various ECMP paths. So that's for the vanilla traffic. Now, in contrast, we can look at what happens if we launch traffic onto a flex algo. And so in this example, PE1 wants to send some other traffic to PE3, but it wants it to be confined to the blue flex algo. So what it does is to put onto the packets the SID associated with PE3's membership of the blue flex algo, 1003. Now, when PE1 did its SPF calculations in the context of the blue flex algo, it realized that its only viable next top neighbor was P1, because P2 isn't even a member of the blue flex algo, so that would have been automatically discounted. And so PE1 sends the traffic only to P1, and P1 in turn realizes that only P3 is the next top neighbor towards PE3 and sends it only to P3. And so in that way, it makes its way horizontally across the diagram to PE3. In a similar vein, PE2 wants to send traffic to PE4 using only the red flex algo. And so it puts on the SID value associated with PE4's loopback address, 2004, sends the traffic to P2 only, because that's the only viable neighbor in the context of the red flex algo. And so in that way, it makes its way to PE4, as shown by those red arrows. And so in fact, this slide illustrates the very first use case of flex algo when flex algo was first invented, which was to achieve plane enforcement in a network where you've got two planes, you put each plane into a different flex algo. And if you want to define, or if you want to confine traffic to a particular plane, you make sure you launch it into the corresponding flex algo, and that means there's no way that it can jump across one of those diagonal crosslinks to the other plane. So this is very good for high availability services where you're deliberately sending duplicate traffic in a live fashion across the network. This is often used for financial market data or broadcast video. So it's a very neat application of flex algo. Now, in this example, each node was a member of only one flex algo in addition to the default grey topology. But of course, in general, a node could be a member of multiple flex algos. So here's another example. So you can see the physical topology shown in grey on the top half of the slide. If you look at the red flex algo on the bottom right, you can see that only a subset of nodes and links are members of it. And so, for example, P5 is not a member of the red flex algo, while it is a member of the blue flex algo. On the other hand, some of the other nodes, P1, P2, P3, and P4, are members of both of the flex algos. And some of the links are members of both flex algos, and some are members of only one of the flex algos, you can see. And so in general, with flex algo, you can have a subset of nodes and links being members of that particular flex algo according to your particular needs. So now we're in a position where we can look at another example. In some cases, you might have different types of traffic using your common network infrastructure, and those different traffic types might have different goals in terms of what type of metric they need. A classic example is where you've got some delay sensitive traffic, and for that you'd want to use a metric proportional to the latency of the link. On the other hand, for things like bulk internet traffic, you want the cheapest cost path, which typically is accordance to the bandwidth of the link. So you want a metric inversely proportional to the bandwidth of the link. And so if you're perhaps merging networks, these two requirements might conflict. With a single IGP topology, you can't set a metric on each link in such a way that it satisfies both of these different styles of traffic. And so this is where flex algo can help a lot. And so in this diagram, we've got a network, and we've got these two different types of traffic. And what's happening is that the bulk internet traffic, which we want to try to make use the high bandwidth links, that's mapped onto the default IGP topology, and that is actually subjected to the metrics shown in the blue colored font. If you look at the diagram, you can see that the high bandwidth links are shown with thicker lines, and those are the diagonal links across the core of the network, while the horizontal and vertical links have lower bandwidth. On the other hand, we want delay sensitive traffic to follow the shortest possible path, and so we map that onto the red flex algo in this example, and the red flex algo has metrics shown in this red colored font. And so that means that, in fact, those two different types of traffic being mapped to different topologies with different metrics actually tend to follow different paths through the network, which is exactly what we want. And so if you look here, the traffic that's the latency sensitive traffic, which is following the flex algo shown in red, that passes straight across the top of the network, P1, P1, P2, PE3, while the bulk internet traffic, which we wanted to follow the high bandwidth links, follows this other path via P5 across the core of the network. And so as you can see, flex algo is giving us this extra degree of freedom, allowing us to map certain traffic to that flex algo such that it can benefit from a different IGP metric setup. And in general, you can choose what style of metric you want for a given flex algo. And so in this example, this particular flex algo has been defined such that it uses a delay metric. And that delay metric can be either statically set if the delay of a given link isn't expected to change much, or in fact it can be a dynamically changing metric according to TWAMP measurements. And so the IGP neighbors are sending timestamp probe packets to each other, and that determines the latency of the link, and that's fed into the metric value that's advertised via the IGP flooding for that particular link. And so that can change as a function of time according to different metric conditions. In general, you can map a flex algo to use either a delay metric or a TE metric or a normal IGP metric according to your requirements. And that gives you enough degrees of freedom normally to be able to have different topologies with different styles of metric sharing the same physical topology. Now, I've been saying a lot about flex algo, and I've been saying, yeah, we map this sort of traffic to that flex algo and so on. But I haven't said specifically how you actually achieve that mapping. So that's what I want to talk about next. And so, in fact, the way we do this is using the property called colors. And so a flex algo is given a particular color, which enables mapping of traffic to it. In a similar vein, actually, it's not only used for flex algos, so TE tunnels, whether they're SRTE or RSVP tunnels, can be given a color to facilitate mapping of particular traffic to those as well. Also, as we'll see later on towards the end of the talk, it's used again in BGP classful transport. So we'll meet colors again when we get to that part of the session. So let's have a look in more detail about how this auto mapping is working on the basis of colors. And so in the example, we've got a network. We're not showing the core routers. We've got two flex algos in use. We've got the red one, which has color 100 ascribed to it. And we've got the blue one, which has got color 200 ascribed to it. And PEY has advertised various prefixes to PEX via BGP. Those actually are tagged with color communities. And so, for example, 10.1 and 10.2/16 have color community 100, while 11.1 and 11.2/16 have color community 200. And these could be plain internet prefixes or could be VPN prefixes. And so what PEX does is, if it needs to send traffic to PEY, perhaps a destination within that subnet 10.1/16, because that prefix has got color community 100 attached to it, PEX automatically launches the traffic onto the flex algo that also has color 100. So that traffic's launched onto the red flex algo, while traffic within the prefix, let's say 11.1/16, that's got color community 200, attached to it, and so that gets automatically mapped onto the blue flex algo because that's got color 200. So as you can see, the colors are a convenient way of auto mapping. Traffic with a given color community is mapped onto the transport that's got that same color. So with that, we can look at a more elaborate example, again using flex algo. And in this case, we're using flex algo within this transport network in the center of the diagram, but also you've got some data centers. And so on the left-hand side, you've got a regional data center, on the right-hand side, an edge data center. This could be in a 5G deployment, for example. And then you've got overlay networks. So you've got these overlays residing on compute resources within these data centers. These can be containerized network functions, hosting things like distributed units and centralized units in a 5G O-RAN deployment. And so each of these colored blobs represents a different slice, a different tenant on this 5G network. And each slice, by the nature of the traffic it's carrying, has different transport requirements. And so in particular, in this example, traffic from the green and purple slices need minimum cost transport once they reach the core, the minimum monetary cost transport, which is the blue flex algo, while traffic from the yellow slice, that's carrying latency sensitive traffic. And so that needs to be mapped onto the red flex algo once the traffic hits the transport network. And so the way we achieve this is by using color communities, which I'll show in more detail in the next slide. And then typically the data centers are, Ethernet, they're Ethernet switches, IP forwarding, spinal leaf arrangement typically, lots of ECMP. And so typically people don't want to extend the transport like flex algo into the data centers. They're just doing plain IP forwarding. And so what you'll have is an MPLS over UDP tunnel carrying, layer 3 VPN labeled packets across the spinal leaf to the DC gateway. So it's the DC gateway that's doing the mapping into the correct transport on the basis of color community. And so we can zoom in and look at how that's working in more detail in this slide. So this is a cross section through that same network where that data center on the right-hand side, we're zooming in on one compute resource. We're zooming in on the green virtual overlay network. And what you've got typically on the compute resources is a virtual router, a software-based router, which has separate VRFs for each slice. So we've got the green VRF highlighted here, and you've got these containerized network functions, which act as CEs from this, layer 3 VPN point of view. So they're the CEs from the point of view of this green VRF. And what you'll have is advertised using BGP is the prefixes pertaining to these containerized network functions. So here in the example, we've got the prefix associated with CNF2. And so you've got a layer 3 VPN label highlighted here, V2. You've got normal route target associated with the VPN. And then very importantly, the color community 200 in the example. And normally this advertisement is mediated by an SDN controller that's controlling the cloud overlay and the associated routing. And so it's going to be advertising that prefix via BGP to the local DC gateway. And that in turn will advertise it to other DC gateways in the network. And then finally, that prefix arrives in the green VRF on the left-hand side. And in so doing, the BGP next hop is changing each time you hit a DC gateway. And so suppose now in the forwarding plane, we have a packet which is actually being sent by CNF1 on the left-hand side. Its destination IP address is that associated with CNF2 on the right-hand side. And so in the green VRF is the BGP advertisement that had been sent across the network from right to left. And so from the point of view of that green VRF on vRouter 1, the BGP next hop at that point is the local DC gateway number 1. And so what will happen is that onto the IP packet will be put the layer 3 VPN label, which at this point is value v2 double prime, and the packet will be placed onto the MPLS over UDP tunnel that goes from vRouter 1 to the local DC gateway number 1. And you'll have the VPN label v2 double prime, as you can see, then UDP header on top. Packet arrives at DC gateway 1, it will remove the UDP encapsulation. It sees this label v2 double prime, and so it knows that the BGP next hop for that is DC gateway number 2. Because the BGP route had a color community 200, that triggers DC gateway 1 to put the packet onto the color 200 transport. This might be a flex algo, it might be an SRTE LSP, the one with color 200. And so the packet's launched with the label or labels associated with that transport, the VPN label as well, shown in green. And so in that way, the packet arrives at DC gateway 2. DC gateway 2 does a lookup on that label and puts the packet into the MPLS OVDP tunnel that terminates at vRouter 2. It's sent to the green VRF and to the destination CNF2. And so overall, you can see in a nutshell that simply by adding the correct color community to the prefix, that triggers DC gateway 1 to launch the packet onto the correct transport, onto the correct flex algo, for example. So you can see the color community mapping providing this convenient mechanism of ensuring that we're using the right transport, even if the start of that transport is multiple hops away from where the traffic originated, way back here on the compute resource in this data center on the left-hand side. So with that, what I'd like to do is to talk about the final topic of today, which is BGP Classful Transport, or BGP-CT for short. And first of all, let's have a look at the problem statement underpinning this. And so now we've got a setup, we've got multiple ASs, we've got PE1 on the left-hand side, and it wants to send traffic to PE2, which is several ASs away on the right-hand side of the diagram. And in each AS, we've got colored transport, we've got color 100 transport and color 200 transport, where color 100 is cheapest cost and color 200 is minimum latency. Now, the thing is, this is the problem statement. When traffic goes from ASBR1 to ASBR2, how does ASBR2 know what colored transport is supposed to use for this traffic, which originated back here on PE1? If we're using BGP-LU between the ASs, which is typically used, BGP-LU does not have any color awareness, and so there's no way of conveying to ASBR2 the desire to use, let's say, color 200 for the packet's journey. So this is where BGP Classful Transport comes in. And so what that enables you to do is to actually extend the color mapping across multiple ASs or other types of domain in such a way that you're not having to expose the internal topology of a domain to any other domain. And like as a consequence of this, each domain can make its own choice of transport technology independent of what the other domains are doing. So one domain might be using a flex algo setup, another one might be using SRTE, another one might be using RSVP TE, and that's perfectly fine. And regardless of what they've chosen to do, BGP CT acts as the glue between those domains. Now, as such, it's a very useful extension to BGP labeled unicast, BGP-LU. I mean, BGP-LU has proven to be a very popular way of scaling networks. People just use BGP-LU between domains and no IGP or anything like that, attempting to cross domains. Sometimes this is called seamless MPLS, and it's quite widespread nowadays in terms of the deployments. And so BGP-CT is very similar in spirit to BGP-LU, except that it's got egress PE, color granularity rather than just egress PE granularity. And so BGP-CT is a very good upgrade to BGP-LU in order to support color-aware transport. And so we can look at how this works. So to give a concrete example, we've got these two different colors of transport in use. And so PE2, associated with its loopback address, will be two different labels, one corresponding to color 100, the other corresponding to color 200. And those percolate via BGP, as shown by those dashed green lines, hopping from ASBR to ASBR across the network. The ASBRs are going to be changing next hop to self, which will change the label value as well, but that's fine. At the end of the day, PE1 sees two different label values for PE2, one corresponding to color 100, the other corresponding to color 200. From PE1's point of view, the BGP next hop is ASBR1. So let's suppose it wants to send traffic to PE1. It will have received service level prefixes from PE2, perhaps VPN prefixes with color 200. And so to ensure that those do use the color 200 transport, PE1 first of all puts onto the packet the layer 3 VPN label, and then the BGP CT label associated with color 200, associated with PE2's loopback address, and then finally labels associated with the local transport, which might be FlexAlgo, might be SRTE, might be RSVP-TE, terminating at ASPR1. ASPR1 hands over the packet. At this point, the top label will be the BGP CT label. ASPR2 sees that, knows that it's associated with color 200, and so uses the color 200 transport to reach ASPR3. Similarly, color 200 will be used for this final AS hop, and so the packet consistently, as it travels between ASs and across ASs, will be using color 200 transports. Finally, let's have a look at some of the nuts and bolts behind BGP CT. And so there's a new SAFI defined for it, regardless of whether you're talking about IP version 4 or IP version 6. The SAFI value is going to be 76. Because we are advertising the same address with different attributes, we need to disambiguate those two versions of that prefix. And so route distinguishers are used to achieve that. And then you've got the label value. This is for the red, the color 100 transports, and then a different label value L2 for the color 200 transport. And in order to convey the actual color, there's a new flavor of route target called the transport target, and the color is embedded within that. So that's a flavor of how the BGP CT modifies BGP to carry this type of color information. So that brings me to the end. Finally, some references for further reading, but thank you for your attention. Now we're open for questions.
Well, Julian, thank you for presenting and for joining us for this Q&A session. And the first question from our community is, it's all fun, everything works great, but at some point things break. Specific to FlexAlgo, what operational tools are available for troubleshooting?
Right, yeah, it's a good question, actually. So first of all, there are CLI commands where you can visualize membership of a FlexAlgo and what metric is associated with a FlexAlgo. You can see what other nodes are members of a FlexAlgo when you're looking on the CLI of one router. But then another aspect which is very useful is that BGPLS has extensions for FlexAlgo. So BGPLS is the method whereby the topology of a network is reported to a central controller, and then the user can visualize aspects of the topology, at the controller level. So BGPLS has been used for quite a few years, just for reporting the, topology of a network and attributes of links, such as the bandwidth of a link. And so with the FlexAlgo extensions to BGPLS, the controller knows what the FlexAlgo membership is, which nodes and links are members of a given FlexAlgo, and then it can provide visualization on that basis, to the user in a graphical form, or it can, have a northbound REST API to, report to, an orchestrator or something like that, if that's interested in what's going on at the FlexAlgo level. So the BGPLS extension is a very useful ingredient as well for the visualization.
Gotcha. Thank you. Our next question is, how different is BGP Classful transport compared to BGP SRTE?
Yeah, they're quite different beasts, I would say, because SRTE is, very much, traffic engineering, and furthermore controller driven. So the usual model is that you've got a controller, computing a TE path, across a network, and then it imposes that path onto the ingress router by, communicating it using the, SRT extensions for, BGP. So it's traffic engineering orientated. BGP CT is more a case of providing glue between different domains, with color awareness, furthermore, for that glue when you're sending traffic from one domain to another. I mean, whether or not an individual domain uses traffic engineering or not is up to you. And as I mentioned, people can make independent choices. So domain one might be just using shortest path routing with FlexAlgo. Another domain might be using, traffic engineering and so on. So they're somewhat, independent of each other, I would say, the BGP SRT and the BGP CT.
Gotcha. Thank you. Our next question is, could IBGP Classful transport be used to add color awareness in an IBGP LU network? And for example, add color awareness without segment routing?
Oh, that's a good question, actually. I should have said, because, colors are not necessarily associated with segment routing per se. And so, in fact, we recently added color awareness to RSVP. So you can create various RSVP TE LSPs and give, different colors to them. And so in a BGP CT deployment, actually, you could have RSVP in one or more domains. You could have SRT in other domains, as I mentioned, FlexAlgo in further domains. And regardless of what people are doing within each domain, BGP CT is providing the glue with color awareness, between those domains. Yeah, so RSVP coloring is something that we added actually in the most recent release. I mean, people are interested in implementations. Actually, BGP CT we added to JUNOS 21.1 and also RSVP color awareness at the same time, in fact.
Got it. In your BGP Classful transport part of the presentation, you were referencing different autonomous systems. Were they all within a confederation managed by the same organization, or perhaps they were across NNI, connected to via NNI, or they were kind of independent autonomous systems? Oh,
right, sure. Yeah, not confederation in the sort of BGP confederation sense, but I know what you mean, like belonging to the same, operator. In the main, that would be the typical case, like it has been for BGP-LU. So if we look at how BGP-LU has been used, that tends to be used in a single operator's network in order to give some degree of scale. So you might have a network with core and aggregation and access domains, and it might be untenable to put them all into one big IGP. And so what people tend to do is to have in some implementations, separate ASs, for each aggregation, each metro, for example, and then another AS for the core. And then between those ASs, they have BGP LU. And so by extension, people could use BGP CT nowadays instead, but for the same overall use case of, this large network that is being, chopped up into these different ASs for scaling reasons. And once they have the BGP CT, they have the color awareness, between those two domains. That said, from the protocol point of view, there's nothing stopping people using it between real, separate ASs belonging to different companies. It's just something that's not happened so much. So certainly it tends to be, within one organization that we see these sorts of things used, more typically.
Very good. Julian, again, thank you very much for joining us for doing this Q&A. We have really good questions. Actually, there are more questions. If you're welcome to answer in the Q&A tab. And with that, again, thank you for joining us.
Thank you very much, Shogin. Thank you, everybody.